All right, nodal analysis. Look, this is really based on the idea of really summing currents at a node. Now, in a given circuit, what we need to do is we need to select a reference node, and typically that reference node is the node that has the most number of branches coming to it. So look, we'll do this by way of an example, all right? So let's imagine I have the following circuit. I've got a current generator sitting here. I'm going to say that's 3 milliamps, okay? Coming across, I've got a resistor sitting here. I'm going to call that a 5K resistor. I've got another resistor sitting over here. We're going to say it's a 2K resistor. And then I've got another resistor, 1K here, and then another current generator sitting here, which we're going to say is 2 milliamps, all right? So that's the circuit that we're going to analyze, and we're going to analyze this using nodal analysis. So look, I'm really saying there are 3 nodes here. I've got this node right here, which I'm going to call the V1 node. So that's the voltage at node 1. There's another node here, which is like node 2, and I'm going to call that the V2 node. So that's the voltage at node 2. And in this node, which is really the 3rd node here, it's got the most branches really effectively coming to it. I'm going to call this basically my reference node, which is 0 volts. So that's the circuit we're dealing with. So look, let's see now at this first node here, we'll call it the V1 node. We're going to sum the currents coming into or out of that particular node. Remember, if currents come in, I'm going to call them positive. If the currents come out, I'm going to call them negative. So looking at this, what do we have? We have 3 milliamps that's coming in. So let's write that down. 3 milliamps coming in. All right, I've got a current going in this direction defined as what? V1 divided by 2K. It's a minus because we're defining it going this way. So that's a V1, and that's divided by 2K. I've got a current going in this direction. That's defined by V1 minus V2 divided by that 5K. So it's a minus, open up a bracket. This is V1 minus V2, and that's going to be divided by that 5K. Is that it? Yeah, I've got this guy, and this guy. That's all there is, and all of that is equal to 0. All right, so that's my first node equation. Now look, I could simplify this a little bit. Why don't we just do this right now, okay? So I could take this guy and this guy over to the other side. So that gives me 3 milliamps being equal to, what have I got? I've got a V1 divided by 2K plus, I've got my V1 minus V2, and that's divided by my 5K, all right? Well, I could go just a little bit further with this, couldn't I? And I could say that, look, let's just collect our terms here. So what have I got? I've got 3 milliamps is equal to, taking this up to the top over here, what would that be? It would be a 0.5 times 10 to the minus 3 V1s. Then I've got this term here, so that's a plus, isn't it? 1 over 5K basically gives me 0.2 times 10 to the minus 3, and I've got V1 of them, okay, or V1s I should say. And then I've got a minus here, haven't I? And once again, this is 1 over 5K, which is a 0.2 times 10 to the minus 3, and that's multiplied by V2. Okay, so look, I can get rid of the milli all the way through in each of these terms here. All right, so this gives us 3 is equal to, now I've got 0.5 V1 here and a 0.2 V1 here, so that's what, 0.7 V1, and then I've got this what, minus 0.2 V2, okay? And I'm really going to say that's my first node equation. I'm just going to simply label that as equation number 1, okay? So let's now look at the V2 node. So here we go, V2 node. And we're going to sum the currents right here. So let's see what we've got. Well, we've got 2 milliamps coming in, haven't we? So let's write that down. 2 milliamps is coming in. I've got this current here, which I'm defining as minus V2 divided by 1K. And then, of course, I'm going to define this current here as V2 minus V1 divided by 5K. So that's a minus, open up the bracket, V2 minus V1. That's divided by my 5K. So that's taking account of that current, and that current. So that's all equal to 0. So we just need to work with this guy a little bit here. All right. So let's do that. So we've got, take these two to the other side, and I have 2 milliamps is equal to, this is my, well, why don't I just perform that division, right? So this is really what? That's really a 1 times 10 to the minus 3. That's V2. This, remember, has gone to the other side, so that's a plus, isn't it? And if I perform that division again, what do I really have there? I have a 0.2 times 10 to the minus 3. That is times my V2. And then I have what? A minus, this would be the V1, which is a 0.2 times 10 to the minus 3. And that is V1. Okay? So once again, we can get rid of the milli part in all of these terms, like so, and what are we actually left with? So let's have a look. So we've got what? 2 is equal to, how many V1s? Well, we've got a minus 0.2 V1s, haven't we? Yes. And then what about V2? I've got a V2 sitting here and a 0.2 over here, so that is a plus 1.2 V2, okay? And that is really my second node equation. I'm going to just label this guy as equation 2. So in a sense, that's the circuit analysis done. It's a matter now of really solving for V1 and V2. And how would we do that? Well, we could write an expression, what, for V2, couldn't we? We could use this equation here, just operate on this a little bit, and we could say that's what, a 2. I'm going to take this to the other side, so that's a plus 0.2 V1, isn't it? And if I divide that by 1.2, that would be equal to V2. So I could put this back into our first equation over here, and then determine what V1 is. All right, putting this in then, we have, looking at this equation here, we have 3 is equal to 0.7 V1. And that's a minus. Let's open up, well, I'll put the 0.2 there, and let's open up a little bracket here. We're going to replace V2 with this. So we have 2 plus 0.2 V1, and that is divided by 1.2. We'll close the bracket. So now we just need to what? We need to really just effectively collect our terms together. So what do we have here? We have 3 is equal to 0.7 V1, and then that's a minus. So I'm just multiplying this out. There's 0.2 times 2 divided by 1.2. So let's do that little calculation. That is a 0.33 recurring. And then multiplying out, that's 0.2 times a 0.2 divided by 1.2. That gives me a minus 0.033 recurring V1s, okay? So collecting my V1s together and taking this to the other side, I have 3.33 recurring is going to be equal to 0.66 recurring V1, and solving this then, we have V1 being equal to 5 volts. Okay, so that's our solution for V1. So if I now want to really determine what V2 is, I just need to put that back into here. And so I can say V2 is really equal to 2 plus, what is this? 0.2 times, what? The 5, which is V1, and that is divided by 1.2. And if you work this guy out, I think you're going to see that that is equal to 2.5 volts. Okay, that's nodal analysis, okay? That's the basic principles of nodal analysis. Effectively, you are summing currents at nodes, and as a result of doing this, you're defining your currents in terms of the V1 node, the V2 node, and if you've got more nodes, you might have the V3, V4, etc. So have a look at this, try this example for yourself, and when you're ready, come on back and we'll look at some examples.